All right, guys, before we get started, are there any questions over any of the assignments so far? Any questions over any of the homework assignments? No, you're good. I had a feeling that might be the case, but just wanted to make sure. So that's fine. Now, simplest form. We've talked about this. We had this in the last note sheet. Radicands, radicals. No, radicals can have perfect powers as factors other than one. It means we can't leave something that can reduce inside the radical. So if we're talking about, say, the cubed root of 16, well, 8 times 2, and the reason we have this is the cubed root of 8 is 2. If we can simplify something out of the radical, we need to simplify it out. We need to get it down in simplest terms. No, radicals can contain fractions. We can't leave it as the square root of 1/2. We cannot have a fraction inside the radical. Doesn't matter what radical it is, we cannot have a fraction in this radical. And the last one's really just saying we cannot have a radical, be it a square root, a fourth root, an eighth root. No radicals, square roots, cubed roots can be in the bottom of the fraction. We need it in simplest terms. We cannot have a fraction inside the radical, and we can't have a radical on bottom. It's fine to have it on top, but we cannot have it on bottom. Two properties of radicals we're going to be using is the product property. Now, the product property states that if we have the nth root of a times b, this is the same as the nth root of a times the nth root of b. And the same thing is also true is that if we have two radicals with the same index being multiplied together, we can rewrite it as 1. Now, our quotient property states that if we have the nth root of a divided by b is the same thing as the nth root of a over the nth root of b, as long as b is not 0. Can't divide by 0. And we can go back and forth between these here. And a lot of times we would, especially with the quotient property, we put them back together if the numerator is completely divisible by the denominator. We can divide it to simplify. And we can look at some of these here using these properties. Now, the first one we have is the cubed root of 12 times the cubed root of 18. Again, we want to simplify it down, simplify it to a single term. Now, some of these, yes, the 30xs can simplify it. Now, with square roots, it can simplify it and leave it in radical form. Anything bigger than a square root, so cubed root, fourth root, fifth root, and above, the 30xs will do it as long as it simplifies completely. So if the cubed root of 12 times the cubed root of 18 simplifies to an integer, a number, without a radical, it will do it for cubed roots and above. But if it has something left inside the radical, it doesn't simplify completely. The 30xs will still give us a decimal answer. It will not give it to us in radical form. So we're going to do these by hand and assume that they can't be done in the calculator so we see how they work. So we're looking at this here, the cubed root of 12 times the cubed root of 18. We would want to see, say, the cubed root of 12, if it can reduce, if we can take the cubed root of it. We're trying to see what times itself 3 times is 12. Well, there's not a number. And if we looked at its factor, so factor tree, the prime factorization, the smallest prime number that goes into 12 is 2. And for us here, our first step would be 2 times 6. 2 is prime, well 6 isn't. 6 is what? 2 times 3, telling us 12 is 2 squared times 3 because we had 2 2's and 1 3. And doing these prime factorizations, these factor trees are going to help us be able to see how these simplify a little bit nicer. So for the first part here, this cubed root of 12, that's the same as saying the cubed root of 2 squared times 3, because 2 squared times 3 is 12. So we can replace that there. Because if we had, say, 2 to the third, well, the cubed root of 2 to the third would be just 2. They simplify. It reduces. Now, we can also do this with 18. 18, our first number would be 2 times 9. And 9 is 3 times 3. So with 18, our prime factorization is 2 times 3 to the second, because again, anytime we can reduce, simplest with cubed roots would be to the third power, but as we see here, with 18, nothing simplifies. 2 times 3 squared, we can't take the cubed root of 2, we can't take the cubed root of 3 squared, we can't take it and simplify it as it is. Questions on this so far? Now, we do need to simplify this multiplication. Since we have 2 cubed roots, 2 like roots being multiplied, we can rewrite it as a single root with what's inside being multiplied together.
May I have your attention? May I have your attention, please? If there's any juniors who would like to meet with the NSU rep, she is in the room 10 at this time. That's any juniors. Thank you.
So we can multiply what's inside. So we can multiply our first one, 2 squared times 3, by our 2 times 3 squared, giving us the cubed root of 2 squared times 3 times 2 times 3 squared. Well, we do have some like terms, like bases being multiplied. Our 2 squared and 2 would rewrite as what? 2 to the third. Our 3 times 2 squared, similarly, would be 3 to the third power. And I'm going to step this all the way out, because at this point we could simplify the cubed root of 2 to the third and the cubed root of 3 to the third. Just as we put it together, we could split it back apart, telling us that the cubed root of 2 cubed, well, our cubed root and third power would cancel, giving us 2. The same thing would happen with 3, giving us 3. I think we could also see from our cubed root of 2 to the third times 3 to the third, each one of those roots in that third power would simplify. And what is 2 times 3? So the cubed root of 12 times the cubed root of 18, even though we couldn't take the cubed roots individually, we can take their products cubed root, because the product of them did have enough factors of 2 and 3 to be able to take the cubed root of it. If there was any roots left over, anything that wouldn't simplify, we'd have to leave it inside the radical. Because the whole goal of this is simplified as far as possible. Here, it's simplified completely. Questions on this here? All right. B, the fourth root of 80 over the fourth root of 5. So we need to simplify this as far as possible. And the main thing that we have, or the main thing we need to simplify for this here, is the fact that we have a radical, a radical in the bottom of the fraction. And then we need to see if there's anything that can be reduced. We can take the fifth root of after that. Now the main theory or property we're going to be using is this quotient property. The fact that nth root of b over a is the same as the nth root of b. over the nth root of a. And we would use this if the numerator, the number inside the radical on top, is divisible by the number on bottom. Is 80 divisible by 5? Can we divide 80 by 5? Yeah. So using this property is going to be helpful, because what we can do is rewrite it as the fourth root of 80 divided by 5. Well, 80 divided by 5 is 16, telling us at this point here we need to take the fourth root of 16. Now, with simplifying and solving, the part of the fact that we have a radical in the bottom of the fraction is gone. We don't have that. We don't have a fraction inside the radical. So the only thing we have left to check with this here and make sure is that there are no perfect roots inside this here, that we cannot rewrite 16, or 16 does not have a number to the fourth power inside there. And one way we can check, especially by hand, is the factors of tree, or factors of 16 prime factorizations. And again, I always start with the smallest prime number and see if 2 goes into 16. If 2 doesn't, 3 would be my next number to check, and then 5, 7, 11. And 2 does work. It's 2 and 8. Well, 8 is 2 and 4. With 4, we have 2 and 2. Well, 2 is prime, so we're done. Telling us the prime factorization of 16 is 2 to the 4th. Which is nice for us here because it tells us that the fourth root of 16 is 2. Because what number times itself 4 times is 16? That would be 2. That also means that we could have plugged the fourth root of 80 over the fourth root of 5 in the calculator to give us an answer. But again, if it doesn't simplify nicely, we have to break it down. Any questions on this here? Next one we're looking at is the cubed root of 4 times the cubed root of 128. Now the cubed root of 4 is not going to work. We can't simplify that any further than that. Mainly because if we looked at 4 prime factorizations, well, 4 is just 2 times 2, or 2 squared. There is no number times itself 3 times. That gives us 4. Square root of 4, yes. Cubed root of 4, no. Now, we also have to look at 128 to see if there's a number times itself 3 times that is 128. There's a good chance there is, but we're going to go on and simplify this here by our factor tree. Since it is an even number, we can start with 2, which is 2 and 64. 64 is 2 and 32. 32 is 2 and 16. 16 is 2 and 8. 8 is 2 and 4. 4 is 2 and 2. So 128 is 1, 2, 3, 4, 5, 6, 7. Is the same as 2 to the 7th power. Because our 2 to the 7th gives us 128. So really the second part we're looking at is the cubed root of 2 to the 7th power. Questions on this so far? Because the whole point of all of this here is to be able to reduce these roots as far as possible so that we can simplify where needed. All right, guys, heads up. Heads up. I know we're close in the end, but again, it's still possible to not pass this class. I don't think you want to see me for another year. So, again, when we're looking at this here, cubed roots, we're trying to find the number times itself 3 times. Now, the second one, the cubed root of 2 to the 7th, we can simplify this. It's how many times is 2 being multiplied by itself? Well, 7. So we could, at this point, simplify this a little bit, because anything times itself, this is 7, the same as 2 to the 3rd times 2 to the 3rd times 2. Well, why did I break it up into 3 different terms? Well, again, we're looking for a number times itself 3 times. 2 to the 3rd times 2 to the 3rd times 2, 3, 6, 7. 2 of these 2 to the 3rds will simplify out, because again, we're looking for a number multiplied by itself 3 times. So one of the 2 to the 3rds would simplify to 2. The second, again, would simplify to 2. 2 of them will simplify out. But since it's 7, there's not a full group that simplifies out, so we're left with 1 inside. Now we can multiply. Well, our numbers outside 2 times 2 is going to give us 4. Now we can also multiply our radicals, because the cubed root of 2 squared times 2. We have like radicals. The indexes are the same. We can multiply what's inside. And what that tells us now is that we have 4 times the cubed root of 2 cubed. Because 2 squared times 2 is 2 to the 3rd. And the cubed root of 2 to the 3rd would be 2. 4 times 2 is 8. Because again, we're trying to simplify this as far as possible. So with cubed roots, we're looking for numbers times itself 3 times. Anytime we have that group of 3, a number times itself 3 times, we can reduce that radical. Questions on this here? Questions on how we got 8? Because a lot of what this is, and especially with this section, is knowing our factors and being able to reduce. Now, if we look at the next one, the 5th root of 192 over the 5th root of 6. Now, what would be very nice if 192 is divisible by 6 evenly. If we can divide it evenly, it's going to make this work out a lot nicer. Well, 192 over 6 is 32. Since they do divide nicely, we can rewrite it, yes sir, yes, as a single expression inside the radical and then simplify. So we have the 5th root of 192 divided by 6. Well, 192 divided by 6, as we just saw, simplifies to 32. So that helped us because now we don't have a radical in the bottom of a fraction or a fraction in a radical. The only thing we have left to look at is the 5th root of 32 if it simplifies. And again, we could try plugging that in a calculator, or we can do the factor tree, which the factor tree helps us see the prime factorization. What times itself? The prime numbers times themselves. And well, 32 is 2 to the 5th, which also means the 5th root of 32 is 2. Because it lets us be able to see how many times a prime number is being multiplied by itself, which lets us be able to reduce this radical, simplify it down. Questions on these here? Rewrite each expression in simplest form, because all these up to this point, we might as well just grab the calculator and said the cubed root of 135 is, well, 5.1299278.4 is not the right answer. I will mark it wrong, because again, we need it in simplest radical form. And what that tells us is that this does not simplify completely, unlike the previous few. So this one here, doing the factor tree, seeing the prime factorization will help us be able to see our cubed roots. So again, we're looking for the smallest number that we know for sure goes into 135. Well, since it does end in a 5, we know it has to be divisible by 5. So if we divide 135 by 5, we get 5 times 27. 5 is prime, 27 isn't. 27 is not divisible by 2, but it is divisible by 3. 27 would be 3 times 9, and 9 is 3 times 3. So our prime factorization of 135 is going to be 3 to the third times 9. This helps us be able to take this cubed root of 135 because we can replace 135 as 3 to the third times 5. And again, we can take the cubed root of any number that's multiplied by itself 3 times by whatever that index is. Now to help us see how this simplifies, we can split this apart. We have two things being multiplied inside the radical. We can break it up as two separate radicals being multiplied together. Now the cubed root of 3 to the third does simplify. Because again, when we're simplifying this cubed root, we're trying to find a number times itself 3 times. And since here 3 is being multiplied by itself 3 times, the cubed root of 3 to the third is 3. Anything that does not fully simplify gets left inside the radical. So what that tells us is that the cubed root of 135 is 3 times the cubed root of 5 times. And we can see here that 3 times the cubed root of 5 is the same as the cubed root of 135. So we know that that is the correct expression. Questions on this here? Questions on how we got to 3 cubed roots of 5? Before we look at the next one, let's look at another one like that. Let's look at the cubed root of 500. Because again, at this point, we wanted the simplest form. There is no fraction in the radical. There's no radical on bottom. So it's just making sure there's not a perfect cubed, a number times itself 3 times. Now, we can do it the way we've been doing it. Or the other option is just start dividing 500 by our cubics to see if we get something that simplifies. So 8, 64, 27, and going up that way. Or we can do our factor tree. Since it is an even number, we know that it is divisible by 2. So we know we have 2 times 250. 250 is still even, so it's 2 times 125. Well, 125 is not even anymore, but it does end in a 5. So it's going to be 5 times 25, and 25 is 5 times 5. So we do have our prime factorization telling us 500, written as a product of prime numbers, is 2 squared times 5 cubed. And as we've seen already and seen up to this point, our 5 cubed simplifies with our cubed root to give us 5. Can we simplify the cubed root into squared? No, we don't have enough 2's, because for us to simplify, we would need at least 3 or a multiple of 3. Because 2 to the third would simplify to 2. 2 to the sixth, that's 2 groups of 3, would simplify to 2 squared, or 4. So we could simplify 2 to the third, 2 to the sixth, 2 to the ninth. Any in between would leave some inside. So we're left with 2 squared, but we won't leave it as 2 squared. We'll simplify that. 2 squared is 4. Telling us that the cubed root of 500 is 5 cubed roots of 4. Any questions on this so far? So again, this is all about simplifying those perfect square, those terms that we can take out. So let's go back to this one here. The 5th root of 7 over the 5th root of 8. In the previous ones we've done, the first thing we look for in these fractional expressions with radicals on top and bottom of a fraction is if the numbers inside of them would divide nicely. Well, 7 divide by 8 nicely. Well, no, 7 does not go in, 8 does not go into 7, an even number. It gives us a decimal. So we can't do that there. So since we can't simplify it that way, we do need to simplify the bottom of this fraction as far as possible, and then try to simplify it out. Well, the 5th root of 8, so 8. 8 is 2 times 4. 4 is 2 times 2. So 8 is 2 to the third power. So even if we wanted to, looking at the factors for 8, 8 is the same as 2 to the third power. We can't simplify 2 to the third, the 5th root of 2 to the third, because we do not have enough factors of 2. How many factors of 2 would we need for that to simplify? We would need 5, because the cubed root of 2 to the 5th would simplify out completely. We need that to have a 5th power, or multiple of 5. On top of this, we just still have the 5th root of 7, because 7 is a prime number. We can't simplify it any further than that. Now, what we're going to need to do to simplify it is we're going to have to multiply it by 1. Specifically, a fancy version of 1. Because it's not so much that we're trying to eliminate or remove. We're trying to simplify that radical. And we're going to multiply it by 1. Specifically, the 5th root of 2 to a power. And the whole goal behind this is to multiply it by the 5th root of 2 so that the denominator becomes 2 to a power, and that power is some multiple of 5. Because if we can get it to 2 to the 5th, well, the 5th root of 2 to the 5th is 2. It will simplify out completely. And that's the goal with this here, is to get that denominator to simplify out completely. But what we're starting out with is 2 to the third power. How many more 2's will I need to add to it to multiply this by to get it to the 5th? How many is it missing? It's missing 2. So what we can multiply on top and bottom of this fraction is 2 to the second power. Because we can multiply the numbers inside. Well, 2 to the third times 2 squared. When we multiply those like bases, we have the exponents. Well, 3 plus 2 is 5, so it will give us that 5th root of 2 to the 5th on bottom. On top, we multiply these here. Well, 7 times 2 squared is 4. And 4 times 7 would give us 28, because the whole goal, we might not end up simplifying the radical out completely, but it needs to be out of the bottom of that fraction. We cannot have a fraction inside a radical or a radical in the bottom of the fraction. So we have to get that prime factorization and then multiply the bottom by any terms that it's missing to get them to have an exponent that is a multiple of that index so that it reduces, it simplifies. Questions on this here? Okay. The other one we're going to look at is this here, the fourth root of 19 over the fourth root of 4. Now 19, luckily for us, is prime. There is no number besides 1 and 19 that multiply together to give us 19. Now 4, we've seen already. We've worked with 4. 4 is the same as 2 squared. And just like before, our goal is to multiply the top and bottom of this fraction by an expression with a radical. So in this case here, our fourth roots on top and bottom, and the number inside of it is 2. We need to multiply this fourth root of 2 squared by the fourth root of 2 to a power so that we get the fourth root of 2 to the fourth. And the reason we want this is, well, the fourth root of 2 to the fourth would be 2. It would simplify. It would reduce. We would not have a radical in the bottom of that fraction. So we have 2 2's. Well, what's the next multiple for after 2? Well, the first one is, well, 4. We have 2 of them. We're missing a grand total of 2. So we have to multiply the top and bottom of this radical expression by 2 squared, fourth root of 2 squared. Well, on bottom, the fourth root of 2 squared times the fourth root of 2 squared would be the fourth root of 2 to the fourth power. We do get that multiple of 4. On top, we'd have the fourth root of 19 times 2 squared. And just like we wanted, the fourth root of 2 to the fourth would indeed be 2. On top, we have this fourth root of 19 times 2 squared. What's inside here? We can multiply together. It's just 19 times 4 times 2 squared, 76. It feels like we should be able to take the fourth root of 76, but fourth root of 76 is just 19 times 2 squared. There is no number times it except 4 times. That gives us 76. Questions on any of this here? Last thing we have is this here. We want to rewrite this in simplest form. Now the issue with these here is the fact that we have a square root in the bottom of the fraction. We cannot have a square root, a radical, in the bottom of these fractions. It just doesn't work. We can't leave it in this form. And main reason for that is we cannot have an irrational number in the bottom of the fraction. That's it. That's the main reason. Now, to get rid of this radical in the bottom of the fraction, again, we're going to multiply this expression by 1. Now, it's not specifically just 1. It's a fancy version of 1. And what we do to get it is we take what's on the bottom of this fraction, 5 and the square root of 3, and we switch the sign in front of the radical. We switch the sign between the two terms. So we have 5 plus the square root of 3. Well, I'm going to flip it. I'm going to take its conjugate and multiply it by 5 minus the square root of 3. Because again, the whole reason we're doing this, and the goal is to get the denominator to not have a radical. So specifically, we're going to look at the bottom of the fraction first, do that multiplication, then we'll look at the top. Well, the first product we have is 5 times 5. which is 25. Then we have 5 times negative square root of 3. Well, that's just going to be negative 5 square root of 3. Then we have the square root of 3 times positive 5 is going to be plus 5 square root of 3. And square root of 3 times negative square root of 3. Well, we can multiply the numbers inside. 3 times 3 is 9, square root of 9. Still have 25 because there are no other like terms. Everything else has a radical. Well, negative 5 square root of 3 plus 5 square root of 3 is 0. These cancel out. Minus. So the square root of 9 is 3. When we multiply these conjugates together, it's going to simplify out any radicals. Simplify all the radicals out. Well, 25 minus 3 is 22. So we multiplied 5 plus the square root of 3 by 5 minus the square root of 3. It simplified to 22. We do not have any radicals left in the bottom of the fraction. Well, we also have to multiply this on top. Well, 5 times 1 is 5. 1 times negative square root of 3 is negative. No like terms on top and bottom. That is as simplified as it gets. Questions on this here? One over the square root of 7 minus 2. Yep. Luckily for us, these all work in the calculator. But at least we know how to do these also. And that's it. Really. (14, 15, 18 through 28 even). 31 through 34. I mean, it was the exact same thing as it was written earlier, but